Hello friends, today, how can we stream a full HD movie seamlessly? Which seemed impossible in legacy networks. So friends, in this video we have shown what are the limitations of wireless channel, how wideband single channel are inefficient for transmission. To overcome, how wideband single channel is divided into small subcarriers and increase efficiency by reducing delay spread. How concept of orthogonality is introduced in FDMA and achieved multifold throughput. Hi everyone, welcome back to the world of 4G.
Previously we have shown how mobility and global connectivity was achieved by introduction of wireless communication. But there are several complexities associated with wireless channels. Multipath fading. Unlike a wired channel, which uses a fixed path, the signals in a wireless channel can reach a user using multiple paths. All these signals known as multipath components may have different channel gain and time delay. This combined effect causes what we know as multipath fading. Delay spread. As a consequence of multipath propagation, the duration of a symbol gets extended. This may interfere with the next symbol. This is called inter-symbol interference or crosstalk. Guard periods are introduced to avoid crosstalk. Frequency selective fading. Signals having bandwidth higher than the coherence bandwidth of the channel faces variable attenuation at different frequencies. This ultimately distorts the signal, and giving rise to frequency selective fading. Complex channel equalization techniques are employed to reduce it. Inter-channel interference. Often signal bandwidth of adjacent carrier frequencies overlap with each other, giving rise to inter-channel interference. Guard bands were introduced to avoid inter-channel interference. All these limitations compounded with the scarcity of bandwidth, gave rise to multiple access technique, Ofdma. Before diving into Ofdma, let us understand multi-carrier wireless transmission system.
Suppose a signal is to be transmitted over a bandwidth B, and carrier frequency fc. Then symbol time for this would be Ts equal to 1 by B. For a single carrier wideband channel of let's say 1 MHz, the symbol time will be 1 microsecond. Given that the delay spread of the channel is of 2 microseconds, the combined symbol time would be 3 microseconds. Which means delay spread occupies 66% of the combined symbol time, thus reducing the efficiency of the channel by 1/3. As delay spread is difficult to control, the effect of delay spread can be minimized by using multiple subcarriers of lesser bandwidth. So instead of having a single carrier of 1 MHz, we divide it into 100 subcarriers of 10 kHz. Each having a symbol duration of 100 microseconds. So a delay spread of 2 microseconds will have a negligible effect over the channel efficiency. This concept is used in FDMA, which uses slowly modulating subcarriers of higher symbol duration. As these subcarriers are modulated with data, they gain bandwidth centered around the subcarrier's frequencies. Guard bands are used to separate them in frequency domain. We can represent this transmitted signal in the equation form as shown here, where summation of individual symbol multiplied with different carrier frequencies and transmitted at radio frequencies. Ofdma or orthogonal frequency division multiple access is a special case of FDMA, where users are provided a set of subcarriers overlapping in frequency domain. However, these subcarriers are specially designed to be orthogonal to each other, which allows them to occupy the same bandwidth without any interference. This in turn negates the use of guard bands. As a result, the subcarriers can be closely packed to increase channel efficiency. Now, before looking at the multiple access part, let's understand how OFDM or orthogonal frequency division multiplexing works, and how it's used in long-term evolution.
In OFDM, high-speed data streams of large bandwidth are split into parallel, slower substreams of lower bandwidth called subcarriers. These subcarriers are centered around frequencies in multiples of 15 kHz on both sides of DC. as the lowest subcarrier is of 15 kHz. Symbol duration, TS, is equal to 1 by 15 kHz or 66.7 microseconds. Consequently, a 1 subcarrier can provide a symbol rate of 15 kilosymbol per second, which is analogous to having a symbol rate of 1 symbol per second for 1 Hz of bandwidth, or half the Nyquist rate. Unlike in GSM or UMTS, LTE supports variable bandwidth as shown in the table. As the bandwidth increases, so does the number of subcarriers in it. Let's take, for example, LTE bandwidth of 20 MHz, which has 1,200 subcarriers and thus a subcarrier bandwidth of 18 MHz. 2 MHz used as guard band. Here we have 600 subcarriers on both sides of the DC frequency. All these carrier frequencies are harmonics of 15 kHz, varying from -9 MHz to 9 MHz. In time domain, these subcarriers will be represented as everlasting sinusoids at these carrier frequencies as shown. However, in order to transmit data over these subcarriers, they are loaded with modulation symbols that represent the constellation points of digital modulation schemes, like UPSK and nth order comms. Also, the symbol duration for each of these subcarriers is always equal to 66.7 microseconds, which means that all these subcarriers have a whole number of cycles in one symbol duration. As we know that a rectangular function can be represented in frequency domain as a sinc function which is centered around DC. When multiplying a signal to a carrier frequency in time domain, signal will be shifts in frequency domain by the same amount of carrier frequency.
Thus we can represent these modulated subcarriers in frequency domain as a series of sync waves centered around the carrier frequencies. Basically, we are having 1,200 such sync waves. There are 2 points to be noted here. Firstly, the subcarriers are overlapping in frequency domain. As we can see, the subcarriers are placed in a manner that all the other subcarriers have a zero component at the peak of one subcarrier. Such subcarriers are called orthogonal. As a result, a mobile can sample the frequency and phase, without any interference from neighboring subcarriers. Orthogonality is achieved by ensuring that all the subcarriers have same symbol duration TS, and the subcarrier spacing is maintained at delta F equal to 1 by TS. Secondly, presence of negative frequencies. It can be explained by the fact that the subcarriers are transmitted below the radio carrier. So friends, today we learned how information is split into smaller subcarriers in multi-carrier modulation, and how efficiency was increased by placing them orthogonally. In our next video we will show how data starts its journey as a stream of bits and are finally transmitted as radio signal. So friends, don't forget to subscribe to our channel, like our videos and comments your views or suggestions. Happy learning!